Millions of years ago, a single step changed everything.
Why did our ancestors stand up and begin walking on two legs? It is a question that reaches to the roots of what makes us human. Footprints frozen in time give us a direct line into the first steps of our story. To understand bipedalism, we travel back millions of years to changing climates and shifting forests. Our primate ancestors were built for the trees, with bodies adapted to clinging, climbing, and leaping. As climates shifted, forests gave way to more open environments. New pressures led to new solutions. The world became a patchwork of habitats, forcing primates to navigate both trees and ground. Scientists proposed many ideas about why bipedalism evolved. Each idea tried to explain different clues in the fossil record. One early idea said standing up helped ancestors see over grass to spot predators or food. It became known as the savanna hypothesis. Research showed that upright walking can be more energy efficient for long distances, an advantage for foraging and moving. Free hands meant carrying food and infants and eventually using and making tools. That changed social life. Walking upright reduces direct sun exposure on the body and improves wind exposure for cooling. In hot climates, that's a real benefit. Bones hold the key. The shape of pelvises, femurs, and footprints all point to an upright gait evolving over millions of years. Sahelanthropus, gated around 7 million years ago, gives early hints that upright posture was already emerging. Orrorin, found in Kenya, had femurs with features consistent with weight-bearing walking. Ardi, at 4.4 million years, was a mosaic. She could move in trees, but also shows adaptations for upright walking. Australopithecus anamensis shows a clear trend toward bipedalism, while still keeping arboreal abilities. The Laetoli footprints in Tanzania are one of our clearest records of early bipedal walking. They show stride, balance, and social groups. Lucy gave us a detailed picture of a committed biped with a small brain but clear upright adaptations. Early hominins were diverse. Different lineages show different mixes of traits, underlining that bipedalism did not follow a single path. Species like Australopithecus africanus and Sediba show continued refinement in walking and hand use. With early Homo, tool use becomes clearer. Hands and feet work together in a world shaped by bipedal motion. Homo erectus shows body proportions closer to ours, built for long-distance walking and running. The spine curves evolved to absorb shock and balance the upright trunk above the hips. The pelvis shortened and widened for upright gait, but that change made childbirth more challenging. Bipedalism brought costs, back pain, joint strain, and a narrower birth canal. Evolution balances benefits and trade-offs. Some researchers suggest bipedalism evolved to free hands for carrying food to mates and offspring, promoting social bonds. Standing upright reduces surface area exposed to direct sun and increases cooling by wind on the body. Some propose wading in shallow water favored upright posture. It is controversial, but offers a plausible niche explanation. Standing tall can also work as a display for mating or status, making individuals more visible to others. In open habitats, the ability to see danger early could make a life or death difference. Being upright helps in reaching food at multiple heights without losing the ability to move quickly across the ground. Bipedalism made coordinated group travel and shared provisioning feasible, shaping social structures. When science measures energy cost, walking upright often shows long-range advantages that matter for foraging and migration. Beyond Laetoli, Other fossil trackways keep emerging, filling the gaps in our understanding of locomotion. Biomechanics labs today test walking mechanics, revealing how our bodies evolved to move efficiently. Comparative studies show that while other primates can walk bipedally for short periods, only humans evolved a habitual upright gait. Carrying infants and prolonged childhoods likely shaped social care and the value of free hands. Tools may have both benefited from and promoted bipedalism, creating a feedback loop between hands and walking. Control of fire and cooking changed diets and daily life, actions that fit well with group mobility and bipedal lifestyles. Bipedal locomotion helped our ancestors spread beyond Africa, adapting to a variety of climates and landscapes. Our upright posture and sweat-based cooling enabled endurance running, an advantage for persistence hunting and travel. Walking on two legs helped shape social roles, cooperation, and the division of labor that defined human communities. Upright posture could also have played a role in attracting mates. Visibility and display are part of the story. Because pelvis shape made childbirth difficult, social care and group support likely became critical for survival. The fossil record is messy. Different species show different adaptations, challenging single-cause theories. Local environments created local pressures. Bipedal traits could have evolved for different reasons in different places. Modern modeling and simulations let us test how bone shapes would affect movement and energy use. Evolution often proceeds by small changes. Tiny tweaks in foot bones or pelvis shape accumulate into big functional shifts. Balance is an engineering problem. Our bodies evolved to shift weight efficiently over a single supporting leg. Walking is cultural as well as biological. It shapes rituals, journeys, and how artists have long used walking as a symbol of journey, change, and identity. When scientists compare predator pressures and habitat openness, patterns emerge that support vigilance and mobility benefits. Researchers debate, disagree, and refine theories. Science advances through testing ideas against new evidence. New imaging and modeling technologies let us peer into bone structure and test walking mechanics like never before. Shifts in diet and the need to transport and share food likely favored hands that could carry and manipulate. Seasonal resource availability encouraged walking between camps and predictable migration patterns. The stages children pass through in learning to walk echo the long process our species took to perfect bipedalism. Walking enabled wider social networks and knowledge transmission, which in turn may have driven cognitive growth. As groups moved, they exchanged tools, genes, and ideas along walking routes that connect communities. Field studies of modern foragers offer a living window into how walking shaped daily life and energy budgets. Robotics and prosthetics borrow from human walking mechanics and, in turn, teach us about our own design. Walking remains central to health and community life, a living link to our evolutionary past. Across cultures, walking carries ritual, economic, and social meaning beyond simple locomotion. Every footprint tells a story. Ancient prints tell us who we were. Modern prints show who we are becoming. Despite progress, questions remain. Why, where, and exactly how bipedalism evolved are still debated. Science advances through excavation, hypothesis, testing, and debate. New finds can overturn old assumptions. From the first upright steps to city sidewalks and global migrations, bipedalism is a defining human trait. No single cause explains everything. Multiple pressures likely combined to make standing and walking the winning strategy. Bipedalism set us on a path that led to tools, language, and culture. The story continues in every step we take. Look back at the long line of ancestors who rose and walked. Each step was an experiment in survival. We walk because walking worked. It changed our bodies, our minds, and our world. It made us human. Credits and selected sources. For more, explore the latest fossil discoveries and biomechanics studies